Yeah. So, good morning, everyone. First, I would like to say thank you for attendance for coming here against amidst this challenging time, this new surge of the cases. So I wish everyone, good health and safety. For this seminar series, I would like to announce that we will go live on Facebook. I highly encourage everyone to please share this content, so that this activity, this meaningful activity, will reach out to your colleagues. Okay, so just give me a second. I will adjust the live streaming. Okay, so the meeting is now streaming live on Facebook. Thank you, everyone. So for today's seminar, I would like to first introduce our two presenters. So I will take the permission to share the screen. So our first presenter today would be Mr. Saswash. So Mr. Saswash he's a master's student. He already graduated from our program, Water Engineering and Management program. Mr. Saswash is interested in researching about water security, green infrastructure, and water sensitive urban design. Coming to today's WEM seminar series, Mr. Saswash is going to share with us his research about improving water security through green infrastructure, an application to selected areas in Kathmandu. And moving on, we also have the presentation of the second presenter, who is Dr. Tuân. So Dr. Tuân has been with us for a while. Dr. Tuân is a postdoctoral research program in our program, Water Engineering and Management program. His research include groundwater modeling, monitoring, investigation, and climate change adaptation. Coming to today's seminar, Dr. Tuân is going to share with us the assessment of groundwater use, impact, and sustainable yield of aquifer system in coastal Vietnamese Mekong Delta. So with that, I will stop share now. And for today's, may I request that the attendants please type in your name following the instruction in the chat box. So with that, I would like to invite the first presenter of today's, Mr. Saswash. Please, thank you. You can start sharing now. Let me make you the co-host so that you can share. Yes, Saswash, you may share the screen now. Thank you.
Thank you, sir. Is my screen visible?
Yes, Saswash, it's visible.
Good morning, everyone. I am here to present on this WEM seminar regarding my master's thesis, which is about improving water security through green infrastructures in urban areas. So this is the general outline of my presentation today. I'll be starting with introduction and giving a little brief about the study area, methodology, and proceeding on to the results and the conclusions of my research. So it is a well-known fact that
Aswat, you can change your display settings to show only one slide.
Oh, okay, yes, sir.
On the top left.
Sorry about that. Yeah, as we know that urbanization in recent times has increased our need to study water management at various scales, and especially at the urban scale. And to ensure water security has been a very crucial step or crucial milestone in order to fight the implications that are brought about by this rapid and haphazard urbanization. And although there have been efforts made globally to combat these water security issues, most of these solutions have been tailored or focused on constructed water management, or what we call gray infrastructures, which on the long run are not very sustainable. And we all know the effects of urbanization, which basically means we have increased impervious surface, which leads to subsequent reduction in infiltration and increases or enhances the surface runoff, which results in a hampered water supply system and leads to water-related hazards such as floods, droughts, and also causes changes in microclimate. So in order to overcome these problems, one of the upcoming solutions and recent solutions has been the focus on green infrastructures or water-sensitive urban design. The basic principle of green infrastructure is to integrate natural system processes into the urban landscape, so that even though the urban area is still dominant with impervious surfaces, we would like the green infrastructure technology or water-sensitive urban design to mimic those natural processes as much as possible, so that the existing or the original water balance can be attained. And green infrastructures, they are mainly there to protect and enhance environmental and economic and social values, with the added benefit of reducing the frequency, the duration, and volume of stormwater runoff, and also reduce the demand for potable water. And as a co-benefit, it also improves the livability conditions of any area, and not just an urban area. And so, as we know, that water security has been common in many years in urban areas, especially consolidated urban areas where population growth and urbanization has been very much high, as opposed to environmental progress. And agricultural land and green spaces have been converted to impervious surfaces, which has again led to increased flooding, reduced water supply. And the problem can be seen as the use of green infrastructures, which through many studies has been shown that it is a viable alternative to gray infrastructures. It is still limited and is not integrated in the planning policies of many areas worldwide. It's only limited to certain areas where the financial resources are available, and it's not widely implemented yet. And the degree of water sensitivity of any urban area depends on how the stormwater is managed in an urban level, and the quantity, the quality determines how secure an urban area is, and it also subsequently helps in defining the resilience and sustainability of that area. So the objectives are to basically assess the baseline water security condition by exploring the dimensions and what indicators of water security, and after that, to select the green infrastructure measures based on the physical characteristic of a study area, and to assess the water security indicators before and after implementing these green infrastructure technologies. So the study area is the Kathmandu metropolitan city, which is approximately at 1,400 meters above sea level and is about 50 square kilometer in area. And as you can see, it is a heavily urbanized area with almost 90% of area being built up and very little in terms of green spaces or blue spaces. And in this figure, you can see the land cover. The land cover area was obtained from OpenStreetMaps. And as you can see, the built up area covers almost all of the metropolitan city. And on the right, you can see the change in urban cover from 1996, which are the parts highlighted in orange, and the current urban cover, which is the purple one. So as you can see, urbanization has been very rapid in the past few years in Kathmandu. And this graph shows the temperature and precipitation for Kathmandu metropolitan city. And as you can see, monsoon brings in the most of the rainfall that falls within the metropolitan city area catchment, and it's concentrated through the months of June and September. And average temperatures range from 29 degrees maximum to about 19 to 20 degrees minimum. And within the study area, within the 50 square kilometer study area, I chose two different areas of interest, which include Shankamu and Bakuzar, respectively 1.23 square kilometers and 0.16 square kilometers. And these two areas are basically good examples of looking at water security issues in Kathmandu, which include urbanization and the conversion of open spaces and green spaces into impervious surfaces. And these two areas of interest also experience heavy flooding during intense rainfall episodes, and they are also in areas of reduced groundwater recharge, which basically highlight the water security issues throughout Kathmandu as well, and not only these two areas of interest.
Shaswat, maybe can you turn on the pointer so that the participants can follow your point easier? Thank you. You can right click and then change pointer to a red dot. Yeah.
Okay. Thank you.
Thank you.
And it is imperative that green infrastructures be implemented in an urban area such as Kathmandu, because due to all the problems faced, such as urban flooding and reduced water supply and pollution, it is important to integrate green infrastructures into the planning policies. Green infrastructures, as discussed earlier, they help mitigating urban flooding issues, which are seen in many parts of the city. And it would also help to enhance storage of rainwater to ameliorate the existing water supply shortage that has been faced by the residents of the city. It would also help in creating more green and blue spaces within the city, so that it would improve the resilience and the livability conditions of the city. And it would also help in mitigating the urban heat island effect. And it would also help in recharging groundwater, which is, as you can see, in many different parts of Kathmandu are the source of many stone spouts in the city, which also hold historical and cultural significance. So the cultural aspect of the city is also being enhanced through the application of green and blue infrastructures. And so data used is shown in the table. Basically, I used elevation maps for both areas of interest: the urban drainage network of Kathmandu, the rainfall data for two stations, the land use map, the impervious percent, and the soil map. So the methodology basically started with a literature review of water security, green infrastructure planning, water sensitive urban design, and water security frameworks. And following from that, I selected some dimensions, indicators, and variables of water security that are able to be enhanced through green infrastructure application. And once those dimensions, indicators were selected, I then proceeded to quantifying all those applicable indicators by comparing them to standard reference values, and then come up with a baseline water security index for those specific indicators. And then after that, I used a tool called the Adaptation Support Toolbox, or the Climate Resilient Cities Toolbox, which is developed by researchers and universities in the Netherlands, which is used to select the possible green infrastructure solutions based on the physical features of the area and the type of mitigation that you want to achieve. So I selected the area of interest and selected my adaptation target and defined the features of the area of interest, such as the scale, the functional land use, the roof characteristic, subsurface availability, etc. And then it provided me with a set of green infrastructures, and I chose applicable green infrastructures based on the location, the makeup of the area of interest, and I did that through analyzing satellite imagery. And after the green infrastructure set was selected, I then proceeded on to modeling its performance in PC-SWIM, where first I developed intensity, duration, frequency curves and imported the urban drainage network and subcatchment delineation, assigning the parameters to the subcatchments, simulating baseline conditions, adding the green infrastructures, and then modeling the performance before implementation and after implementation. So the baseline results are shown in the screen. Basically, for the water availability indicator, we require 135 liters per capita per day of water, which is a baseline data, and currently available is 35 to 37 liters. And as you can see from the scale, it is on a scale of 2, which is relatively fair, but still not good enough. And the blue-green spaces for both these area of interest, as you can see, are close to none, only 0.67% in 𝐤𝐴𝐺𝐻 and 0% in 𝐵𝐴𝐺𝐻. And this data was obtained from a study done by the United Nations Development Program, on where they developed an inventory of green and blue spaces within the metropolitan city. And so the baseline results for both areas of interest, the IDF curves are shown in the 2 different figures. In the absence of hourly rainfall, I had to apply the Monod equation in order to obtain the IDF curves. For Monod equation, you require the daily data, and since only daily data was available, I had to use the Monod equation. And after the curves were developed, I ran the model for baseline results, and for 3 different return periods of 10-year, 20-year, and 50-year. And as you can see, as expected, the 50-year flood has higher runoff rate than the 20-year and 10-year flooding. And in the tables below, you can see the number of manholes flooded and the surface runoff, which is expected to be higher for a larger return period event. And so the selection of GI measures, which I did it through the adaptation support tool, the climate resilience capacity, these are the parameters that were to be defined within the tool. So my major focus was fluvial flooding here, and multifunctional land use was set to important because in a very consolidated urban area, it is important that whatever space available we have to use it for many different purposes and not just a single purpose. The scale level is neighborhood scale, since it's a very small area under consideration. Existing space types for both areas mostly include paved surfaces, undeveloped land, green, gray, sports and playgrounds, and building footprints. Subsurface availability was set to low, and roof characteristics were basically roofs that were less than 35 degrees in slope and flat roofs in the area. Soil type for 𝐤𝐴𝐺𝐻 was sandy soil, but for 𝐵𝐴𝐺𝐻 was clay soil. It was obtained through the soil map of Kathmandu Metropolitan City. And the slope for 2 areas of interest, the first area was a sloping area, and the second one was a flat area on low ground. So this is the adaptation support toolbox window, where on the left, you select all those features for your area. You can outline your area like this, and then you just choose the types of features that are closest to your area of interest. And basically, these polygons, these boxes that you see within the area of interest, these are the potential locations where these green infrastructures can be implemented. And this was solely done through looking at aerial imagery and looking at where there were open spaces large enough to accommodate these green infrastructure measures. More efficient methods can also be used, but for my research purpose, I just resorted to analyzing these satellite imagery and looking at these potential areas, such as open spaces or large roofs where I can implement these green infrastructure measures. So once you select those areas, you get an option of all these applicable green infrastructures, and these are arranged according to score based on the properties that you feed for your area of interest, but I only chose the ones that were applicable to my study area based on the urban makeup and based on the applicability. So basically like green roofs and then rain barrels were more applicable than hollow roads and infiltration of fields for my area. And the similar approach was done for 𝐈𝐦𝐻𝐫𝐸, the other area of interest. The same properties were selected on the left, which gave me a selection of options, and selection was done based on the urban makeup of the area. So these were the GI measures that I chose for my 2 areas of interest, which included wet pond, green roof, permeable pavement, rain barrel, and bioretention cell. So this is the 𝐶_SWIM model. Since there was an unavailability, or should I say lack of fine scale DEM, which for urban areas we require DEM in a centimeter scale resolution, but the least I could generate was a 7.5 meter DEM. So I had to first make Thiessen polygons out of these manifolds and then run a Voronoi decomposition tool within the 𝐶_SWIM model to come up with the subcatchments. And so as you can see, like after implementing the GI, the selected GI, which you saw in the previous slide, for 3 different return periods, the system showed a 10.3, 10.34, and 10.46% reduction. Now, this reduction does not seem very large, but some of the selected subcatchments where the large-scale GI measures were able to be implemented, the results are in the following slides, but the rest of the subcatchments were also reinforced with only rain barrels. And rain barrels, since they are smaller in comparison to our other counterparts, such as rain gardens or permeable pavements, the decrease in performance can be attributed to the smaller scale or smaller size of those rain barrels. So there are 5 different subcatchments which I selected to show the performance of the green infrastructure. So for subcatchment 1054, WP is wet pond, and as you can see, wet ponds were quite effective in reducing the runoff for all 3 return period rainfall events. Similarly for 1056 for green roofs, not much reduction, but still there was a reduction in the runoff. In a combination of green roof and permeable pavement, we could see much more significant difference in the runoff. Same with permeable pavement here, and for wet pond in subcatchment 1133, there was a significant reduction in the runoff. As you can see, about 87% for all 3 return periods. And so from the baseline, we had 35 to 37 liters of water availability, and potential available water for the area of interest increased to 195 liters. Now, this 195 is not considering the runoff reduction or like the water storage from the large scale GI measures, but it's only for the subcatchments where the rain barrels were implemented. So the volume of water stored through those rain barrels was then converted into the amount of water available for usage, and the potential availability reached to 195, which is a very high score in the water security index. Similarly, for blue and green spaces, it increased from 0.67 to 1.54. And similar analysis was done for 𝐈𝐦𝐻𝐫𝐾 model as well. You can see the GI implementation reduced flooding by 25% maximum, and 24% and 23% for 20 years and 50 years return period. Similar thing was done for selected catchments were enforced with rain barrels and permeable pavement combinations, or just a rain barrel or green roof combination, and they perform well in reducing the flooding for these subcatchments. The maximum being 96% for a 10-year return period in subcatchment 2, which included the combination of rain barrel and permeable pavement. And for this area of interest, the potentially available area increased from a baseline of 35 to 37 to 85 liters, which improved in the water security index from a scale of 2 to a scale of 3, which is also, according to the previous slide, only based on the amount of water that was stored using rain barrels and not the large-scale green infrastructures such as rain gardens and permeable pavement. The blue-green spaces also increased from basically 0 to 1.54% in this case as well. And a life cycle cost was done through the same adaptation support toolbox, which gave us the construction and maintenance cost for all the measures that we apply to our area of interest. And looking at the life cycle cost per unit, rain barrels were had the lowest life cycle cost per unit, and permeable pavements had the highest life cycle cost per unit for both the areas. So in conclusion, the potential changes in water security indicators was done through the application of green infrastructure in this research. As we saw in the slides before, the the water security index in terms of per capita water availability increased from 2 to 5 and then 3 to 5 for 𝐚𝐭𝐿 and 𝐕𝐴𝐺𝐻 respectively. Green spaces or green-blue spaces increased for both areas of interest, and permeable pavements and wet ponds perform better than other green infrastructures such as green roofs. And the LCC analysis showed that due to the low investment cost and low maintenance costs, rain barrels were the best choice if every household is considered within the AOI. And it can also be concluded that green infrastructures are an optimal solution to improving the water security of any urban area. And but in my research, I only focused on water availability and reduction in flooding. But as we all know, green infrastructures can bring about a host of other co-benefits, such as temperature regulation, air quality improvement, enhanced biodiversity, and improved groundwater recharge, carbon sequestration, which can be quantified through other approaches as well. And green infrastructure implementation is valuable and important in order to strengthen the resilience of urban areas, in order to increase their sustainability. And it is mostly important for areas where urbanization is done without any regard to the environment, and developments are done without considering these environmental implications. There were certain limitations for this research, such as for example, groundwater flow was not considered. Climate change scenarios were not considered, which can also be integrated into the research. And since I worked on an urban scale, high resolution DEM would have been much more better in analysis for delineating the subcatchments. So due to that coarser resolution DEM, those nuances of the urban areas were not able to be captured accurately. Thank you.
So thank you, Saswat, for providing a very insightful and informative presentations looking at very interesting angles of green infrastructures and nature-based solutions on these terms. Okay, so with that, I would like to open the floor for questions for all the audience. So anyone, if you have questions for Saswat, please unmute yourself. Thank you.
Yeah, Dr. Locke, can I ask?
Yes, please
Hello?
go ahead. Yes, please go ahead. Sorry.
Yeah, hello, I'm 𝐓𝐡𝐫𝐞𝐫 from WEM, PhD student. Nice presentation, Saswat, and nice work also. Yeah, Saswat, can you hear me?
Yes, I can hear you.
Yeah, I have one or two questions, but interlinked with each other. Yeah. So you have shown that you took two case locations like 𝐒𝐭𝐬 and 𝐵𝐴𝐺𝐵𝐺𝐴. So if you see on the map also in 𝐒𝐭𝐬 there is a river, yeah, and you haven't taken the influence of river flooding as you are more concerned about pluvial flooding, more stormwater flooding, yeah.
Yes.
So one side you haven't taken the river, or you have that is your limitation of your study, that you haven't considered fluvial flood. But when we see your idea of curves, or when we see the scenario that you have taken up to 50 years. But generally in urban flooding, 2 years is the most frequent flood, 2 and 5 years flood, yeah, and 10 or 20 years would be the maximum, because if 20-year floods is there, then it will surely flood in urban areas like Kathmandu. So if you have seen recent news also, like half an hour rainfall has also caused flooding in 𝐵𝐴𝐺𝐵𝐺𝐴 area last 2 weeks earlier. Yeah. So
yes.
How do you justify that your work for 50 years flooding that you have shown? Because 50 years, obviously there will be flood for urban areas like Kathmandu. And why didn't you take the most frequent like 2 years and 5 years?
Thank you, Saurav.
Yeah, I considered the 10-year, 20-year, and 50-year return period to cover sort of the middle spectrum, to see like how the GI would be effective. Like based on literature, it was known to me that green infrastructures are not very effective in controlling larger rainfall events of larger return periods. But in order to see whether in order to see how effective it was, I just took the middle bracket of the 10, 20, and 50 year. It was already known that 2 years and 5 years return periods rainfall can be controlled using GI. I just wanted to shift that bracket into a middle bracket of 10, 20, and 50 years. That is the only consideration that I took.
Yeah, thank you. But my recommendation is, if you check with 2 and 5 years, then your when you use your GI, your results, if you see your results, like there's no difference between 10-year and 20-year, yeah, in runoff. Oh, sorry, 50 years, just 10 point something and 10 point something. So if you use 2 and 5 years, that difference you can see very closely.
Thank you. Okay.
So,
thank you, Saurav, for your question and recommendation.
Thank you, Doctor.
So do we have any other questions?
Hello, Saswat.
Hello.
Yeah, can you hear me?
Yes, I can hear you.
Yes, Shashwat. First of all, I would like to thank you very much. Your presentation was very nice, and I would like to know that what is the significance of your green infrastructure to reducing the flood? Like how much you can reduce the flood in your area? Because as much I understanding the Nepal, like you have done a study in the Kathmandu part, these are the hilly regions. So how can you reduce the flood in these areas? What do you think on this point? Like what is the significance to reduce on your green?
Yeah, well, basically for my research, I only considered, as you saw, 2 areas of interest.
Yes.
So in those areas of interest, we saw respectively about 10 to 20% reduction, right? But if we were to, like, since I did not consider the entire 50 square kilometer of the metropolitan city, right? So if we were to apply the same approach that I used for these 2 areas of interest and apply it to several other catchments within the metropolitan city, then I think it would be like a cascading effect, and the cumulative effect would help in reducing the flooding issues, and also at the same time strengthening your water supply issues, because as you can see, like through that application of rain barrels, we were able to see an increase in the amount of available water for usage. So I only considered 2 small areas of interest, but if the same approach can be applied to several other such areas of interest within the Kathmandu metropolitan city and subsequently the Kathmandu Valley, then I think the application of these green infrastructures would actually help in reducing flooding and improving the water supply as well. And like as I told you earlier regarding the co-benefits, when this will be expanded from a 1 square kilometer area application to a much wider application, then the co-benefits can also be seen very clearly, I believe, and it will contribute to the overall resilience and the sustainability of the urban area.
Thank you very much, Shashwat. I have just a little bit more questions on this point only. So what do you think, like your study can help in the dry part of the Nepal, because the dry part of Nepal is the most vulnerable to the flood, as you know that. So if you can extend your study area for the whole dry part, some other researchers can extend, government can apply your research, what they can, like you will be able to reduce the whole flooding in the dry part as well as something, because dry part are the most important area for the flood studies. So what impact you can see with your research for the whole dry part?
I believe that if we are to select a larger domain such as you suggested right now, we would have to expand our domain of green infrastructures as well. Like we have to go from small scale solutions such as rain barrels or wet ponds or green roofs into much larger, into the larger domain of those nature-based solutions. So we can maybe introduce interventions at a watershed or a basin scale rather than just a small urban scale, if we are to control those flooding issues like you mentioned.
Thank you very much, Shashwat. It's very informative to me.
Thank you.
Okay, so thank you, Shashwat. May I request you to share your slide?
Yes, sir.
Okay, so with that, I would like to say thank you, and also Sunu and Saurav for a very interactive discussions. Actually, this is exactly what we're looking for. What keep in mind for organizing this WEM seminar series. So for today's WEM seminar series, we're very happy to welcome not only our students, but also alumni and also the prospective students. I can see that Ms. Ansita and then also Antif Tanvir, who is our prospective student. So we're looking forward to welcoming you here to our WEM family. And I'm very delighted to introduce to you all that Professor Tan Van Hoan, or also known the name as Rebecca. So she's a associate professor in Fangchia University, a very close collaborator of us, WEM. So may I introduce Professor Rebecca to share something about, we're very thank you for having you joining us today. Professor Rebecca?
Yes, can you hear my voice?
Yes, we can hear you clearly.
It's clearly, right?
Yes, thank you.
Nice to meet you all. My name is Len. I'm from Fangchia University in Taiwan. And it is my first time I attend in your lab seminar. So I also take a look some of your web seminar in the fan page Facebook. So I see all of your activities really active. So this time maybe I would like to ask all of our students in our lab need to learn from your lab, because actually as the reason Taiwan is coronavirus it is outbreak, so that we just stop every activities in the office and in the university. So maybe in September we can start our semester. So we will ask our students to join your lab seminar together. So both lab can ask or can discuss anything related to your research, or also is related to our research. By the way, I would like to invite Professor Sankam in AIT. In September, we have a virtual meeting for the Open Geospatial Consortium. That is one of the organization in US, and we are one of the principal member. So we would like to invite Professor Sankam as one of the keynote speaker, representative for Thailand AIT. Is this okay for you? Are you available in September?
Yeah, Rebecca, good morning.
Yes.
Yeah, it's nice to see you here again. Yeah, I'll be very happy to accept your invitation for the keynote speech. Yeah,
Yes.
thank you.
Thank you for your accept. So we will send for you the invitation by email. Thank you so much. Yes.
Thank you.
Thank you, Professor Lo.
Yeah, thank you, Dr. Rebecca. And we've been working closely in developing a partnerships between AIT and WEM, in particularly with FCU in geospatial research. So we're really looking forward to more interactions with you in the future.
Also send us MOU.
Yes, definitely. Yes, we are working actively on that. So I will soon communicate with you after this seminar. So with this, may I request all the participants to turn on your videos so that we can have usual, group meetings with our photographer over here, Mr. Roel. So
thank you.
Follow his lead for the group photo session. Thank you. Maybe you can unmute yourself and give us instruction. Thank you.
Okay, hello, good morning. Please open all your camera and smile in front of your camera. So we have 2 slots of shot. So first slot is, so smile. Okay, second. Everybody smile. Okay, thank you very much, and bye.
So thank you, Roel, very much for being our very reliable photographer on this seminar series. So with that, I would like to return the floor back to our second presenter, Dr. Tuấn. You may start your presentation now. Thank you.
Okay, thank you, Dr. Lok. So very nice to be here today. And for me, I feel very happy because during my even the master or PhD study, I don't have much chance to join some activity like a very too quick, right? We have the one seminar per 2 weeks, so I think it's very good for students and so other can discuss about the result, the methodology, and the issue. So thank you, Dr. Lok, for inviting me for today. So I will share my screen and start with my presentation today.
Yes, please, Dr. Tan, please go ahead and share your screen. Yes, we should see your screen now. Thank you.
Sorry. Okay, so today I will present a part of my PhD research. Actually, I just graduated in the Chulalongkorn University in the water resources engineering department in just 1 year before. So today I will share a part of my study. So focus on the assessment of the groundwater use and sustainable use in the aquifer system in the coastal Mekong Delta, Vietnam, with the case study in the Tra Vinh province. So my presentation, sorry. Okay, so my presentation today including 4 parts: introduction, conditions of study area, the method, and also result and discussion. So I will quickly brief the first part. Okay, so as below, 2/3 of the global population is within the 400 kilometer in the coastal line, and it's cover only the 10% of the Earth's surface. And in the coastal line, the people rely mainly on groundwater for domestic use, industrial, or even the agriculture. So that's why it has been becoming the importance of groundwater management and the understanding about groundwater. Mekong Delta, one of the big basin, the alluvial basin in the
Hello, everyone. Are you still there, Professor Sangam? Hello, Sanjeev. Can you hear me?
Yes, sir, I can hear you.
Yeah, I think let me call Dr. Tan. Maybe some technical issues with the internet.
Yes, sir.
Yeah, so sorry everyone for the technical issues. I'll call him immediately.
sorry.
Yeah,
Yeah,
hello,
sorry.
Dr. Tan. You came back already?
Yeah. Maybe I think the internet in my room is maybe have some problem.
Yeah. I was about to call you. Yeah, you can start share the screen again. Thank you.
Okay. So this is the answer. So can you see my screen?
Yes. Thank you. Yeah, we were about to catch you up to the point of
Okay.
Mekong Delta. Yeah. Thank you.
Okay, so in the Mekong Delta, we know because of the increasing of the groundwater demand, so the over groundwater abstraction is got many issues on groundwater system, like dilapidated groundwater storage, the saline water intrusion, or land subsidence. So the question mark here is how to reach the achievement of the sustainable balance between the demand and the water supply. It becoming the major challenges in the Mekong Delta. So groundwater in the Mekong Delta, I think this was exploited since the early 2000 with a small number, but has increased fastly. So until the 2010, the report does around maybe 500,000 wells covered 1.9 million cubic meter per day of the whole entire of the Mekong Delta. So you can see the graph in the right hand side. So the increasing of the groundwater abstraction from 2000, you see in 2010, it's maybe around 5 times. So, however, the research on the groundwater in the Mekong Delta, even about groundwater pumping, the sustainable use is still used maybe very old concept. Most of the research focus on the safety with the limited factor of the supply, economic, or even the quantity. Actually, now we just only like a specified drawdown of the groundwater level to define the sustainable use of the groundwater, like a limitation of groundwater abstraction. So in the research, we want to fulfill some gaps of the previous research on the understanding of the groundwater use in the Mekong Delta, and so the sustainable use with some new approach of the sustainable concept. So we have the three objectives. One to focus in the research. The first one, we try to explore the pattern and the distribution of the groundwater use, and the second one, assess the current situation of the groundwater aquifer based on the field survey and so groundwater models. And the last one, we try to assess the sustainable use of the aquifer system based on by developing the sustainable model. So I will each bit about the study area. So as we see the picture of the whole Mekong Delta. So the study is the coastal province located between the two big rivers, the river mouth of the Mekong River Delta. So as we know, during the dry season, when sorry, can you still hear me well?
Yes, yes.
Okay.
Yeah, please go ahead.
So yeah, sorry, during the dry season, when the flow discharge in Cambodia to Vietnam is declined to the 2,000 to 6 cubic meters per second. So the saline water from the sea is go inland. So in the coastline, most of during the dry season is the saline water. That's why the people have to rely more on groundwater in terms of the domestic use or even the agriculture. So the Chavin province is a coastal province covered more than 2,000 square kilometers with the very flat. The topography is around 0.6 to 1 meter, cover 66% of the study area, and only few percent is the urban area and the sand dune area with the high elevation. And the annual rainfall in the province is quite high. It's around 1.8 thousand millimeters per year, and the temperature is around 26 Celsius degree. The population in province is around 1 million persons, cover around 268 households. So in this province, the main activity of economic is the rice planting and perennial plant like a coconut or other, and aquaculture, and so the industry. The next slide would like to say about, I think the main slide would like to say about the structure of the aquifer geology and in the Mekong Delta in this province. So we send a highly heterogeneous stratigraphy by transgression and regression event in the past from the Neogen and until the Holocene periods. We will see here the aquifer system of the study area separated by the 8 aquifer and 8 aquitard. So the aquifer consists of the lithology by the sand, gravel, and pebble, and the aquitard mainly is clay, very thick clay. So the shallow aquifers have low water quality due to the direct interaction with the surface water and also the sea. About water supply in this province, the people do 3 sources of the water: rainwater, surface water, and also groundwater. And in 2010, the report does around 245,000 cubic meters per day for groundwater supply in the whole province, with the main purpose is the domestic use and a little bit for the agricultural activity. And the third aquifer, upper and middle Pleistocene, the main aquifer for exploitation is covered more than 70% of the total exploitation. However, have only 121 abstraction wells is under license, cover only 61,000 cubic meters per day. So, and another amount of the ground abstraction is under unlicensed. So the wells belong to the farmers. It's like the own well or the people. They dig by themselves, they manage the pumping by themselves. So the information is still like very unclear. So in this research, I'm going to show the main thing here is the framework research. So firstly, we have the like a big campaign of the electricity conductivity to define how the distribution of the saline water and fresh water in 3 top aquifer. And the second one, we use the socio-economical questionnaire to analyze the pattern and the distribution of the groundwater use and also the surface water use for different purpose in province. Then we use the groundwater model to simulate the flow and also the salinity transportation to assess the impact on the aquifer system. And then based on the calorimetric model, we develop the sustainable model and use the sustainable yield criteria based on the unconsiderable impact based on the level statement level and so salinity concentration. And we will carry out the sustainable yield at the end. So for the field survey, you will see the map in the right hand side. Is so the province was separated by 3 zones: the northern, the middle, and the coastal zone. So the zones were separate based on the distribution of the groundwater salinity and also the surface salinity and also the GDP per capita of the totally more than 60 communes of the province. So at the end, we select 9 communes for conducting the survey. So the distribution of the questionnaire you can see at the map, and so the number for three zones of the province. Totally, we conduct around 419 questionnaire. So for groundwater development in province, firstly we use the regional groundwater model of the whole Mekong Delta as the baseline to develop the local groundwater model in Trà Vinh province to input the boundary condition. Then the other input parameter like conductance, recharge, and also groundwater pumping we use from the survey, and groundwater recharge we have the 5 locations for the testing the infiltration capacity. Then we use the soil balance method to estimate the groundwater recharge, and we develop the map of the potential of the groundwater recharge. Then we input to groundwater model. For the river conductance, because in the Mekong Delta, the top layer is the very thick clay, around 20 to 30 meters. That's why the interaction between the river and the aquifer is seem to be not too high. That's why here we apply the number from the survey of quite a long time ago, 20 years ago, of the USGS to interpolate between the river section or even the canal section. So the time of the simulation is 25 years from the 1994 to 2018, divided into the 300 thread per year. It's a monthly thread. So the calibration of the both groundwater flow model and the salinity transportation model based on the monitoring network. The upper picture shows the network of the groundwater level, and the below one, so the point. As you remember that I mentioned about the EC campaign. So after the EC campaign, we can develop the map of the saline water. Then based on the interface between the fresh and saline water, we intune the equipment to observe the salinity concentration. And based on 2 years of the record, we use the 4 points for calibration in this research. So here the result of my research. So based on the survey, the estimate, I want to show the role of the groundwater compared with the total use in the during the survey. So in the northern part, we see around more than 60%. The domestic use it depend on not depend on the groundwater, and around 20% they use both groundwater and other, and only maybe around 15% totally use the groundwater. So you can see in the coastal area, mainly I think more than 90% completely dependent on groundwater for the domestic use, even in the rainy season, because this area affected by the surface saline water intrusion. That's why the saline water distribute all the time. That's why groundwater is the main source of the domestic use. Only a very few households they have to store the rainwater if they cannot access to the tap water, or even they don't have the money to dig the own well. So for agriculture, it's the same. I think the same trend like in for domestic use. The coastal area also mainly depend on the groundwater during the dry season. However, the crops is mainly like the orchards or some like annual crops like watermelon, chili, onion, a part of the aquaculture. For the food crops or perennial crop, with a huge number of the planting, the farmer they don't use the groundwater for irrigation. So the total estimation of the groundwater in the 2018 for the whole province is like around 346,000 cubic meter per day, and only the coastal district covered 23%, and the middle part cover more than 50%, and around 50% for the northern part. And mainly here we see the focus is for domestic use. But the domestic use here, it's the behavior of the ground use in the Mekong Delta. It's not only for drinking, cooking. The people also use a part of the groundwater for gardening. Gardening for the garden is surrounding the house. That's why I think the amount of the domestic use here we see is higher than the irrigation or even the aquaculture. So we also use the mapping by combine the survey result, statistical result, and also the satellite image to mapping the groundwater use distribution in the dry season of the 2018, and so estimate backward to back 25 years about groundwater use in 3 zones. So you can see in the right hand side, see the time series groundwater use during the dry season of the 25 years for three zones. So the coastal reached to the almost more than 200,000 cubic meter per day, and the northern part is now only about 23,000 cubic meter per day. So based on the survey, we also find the issue of the groundwater definition and also the salinity of the water by the pupil using the groundwater. You can see the number of the based on the survey. So for the salinity water in the northern, 40% of people they have faced the saline groundwater, so they have to stop pumping water, or they have to change to another source of water like rainstone harvesting or use the surface water. And the number is the same in middle and coastal zone is now 28 and 29%. However, about the groundwater definition, it's mainly focused in the coastal zone based on the high density, also the high rate of groundwater pumping in this area. Here I would like to show in the and the very station of our supply with the huge number. That's why after this, it make the groundwater level in this area So the size
Hello, is everyone still in? Professor Sangam? I think Dr. Tuấn again have problems with the internet.
Yeah.
I think, yeah.
Yeah, we cannot hear him.
So let me check on Dr. Tuấn if he can join again. Please allow me a couple of minutes.
come on.
Yeah, maybe he's on, so you can call
Sorry.
him. You were disconnected, Dr. Tuan, so you can share again.
Dr. Tuấn, maybe you can turn off the video as well, just to save some bandwidth for, yeah, because I think today's internet is really struggling.
Sorry.
Yeah, you can start sharing again, please. Thank you.
Yes. I think the internet. So just follow this slide.
Dr. Tuấn, maybe you can share the screen again. We didn't see your screen yet.
Oh, okay. You can see my screen.
Yeah, now I can hear you.
So I can continue this slide.
Yes, please.
Okay. So here I would like to show the distribution by the time, the temporal and spatial of the groundwater level in the study area. So the left-hand side shows the groundwater level distribution of the third aquifer in March 2018. So the definition cone focused in the middle part, and also some point the coastal part is mainly at the groundwater supply station. So with the big number, more than maybe 5,000 or 10,000 cubic meter per day in one point, it makes the groundwater level drop. As you can see in the right hand side in 2008, with the big station in the middle part, it makes groundwater level drop around maybe 6 meter. And as you also see the time series of the 3 point represent for 3 parts of the study area during after 25 years. So you can see first maybe 8 years, the groundwater level keep like stable, not change much. But after 2000, when the groundwater level start to exploit in the Mekong Delta, groundwater level start to decline and decline faster after 2005, even until now, around be a half of a meter per year. And the next slide shows about the distribution of the saline water. So in the campaign, totally we measure around more than 700 points divided by 3 aquifers, but mainly focus on the third aquifer because it's cover 70% of total groundwater abstraction in Trapping province. So based on the number of points, we use the breaking method to interpolate the distribution of the TDS to represent for the saline water. So in Vietnam, with the TDS 1,000 milligram per liter, we consider the interface between the saline and the fresh water. It's the standard for supplying the drinking water. So you can see, I think it's a different thing with the other coastal area. You can see the coastal area is the fresh water, and the inland is the saline water. But the concentration is around maybe 3,000 to 6,000 milligram per liter only, not equal the salinity concentration of the sea around 35,000 milligram per liter. So have some research done before, and during this time explain about the source of the saline groundwater in the Mekong Delta, like the parallel saline, based on the regression in the past. Actually, it's still like not much evidence. So a lot of research still working on that. So based on our survey, we can so that's the freshwater is distributed in the middle and in the coastal part, but in the northern part, mainly the saline water, but not like a high concentration. And based on model, we also export the groundwater balance of the aquifer system here. We only show 3 top aquifer water balance. So you can see with the high groundwater abstraction, 38% of the total ground abstraction is from the storage. That's the reason why it's make the groundwater level decline year by year. And also here you see the recharge only contribute 35%, and river contribute only 10% of the total recharge to the aquifer system. Then we move to the sustainable use estimation. So here we, based on the assessment of the groundwater system in the area, we would like to propose the criteria of the sustainable use to limit the unconsiderable result of the groundwater pumping. So the first thing we want the pumping amount can lead the groundwater level reach to the equilibrium state, and also control the salinity movement. So this is the figure. So the sustainable model run to the 2050. So after 5 years of the reduction of the groundwater pumping, we get the stable of the groundwater level in, I think in here I show only 2 points of the northern and also the middle point. You can see in the seen in the last slide. So the amount of the groundwater abstraction here is considered the safe use of the aquifer. However, in this research, we would like to add the concept of the control the salinity movement. So we can see in the picture, the figure here. So you will see the pink color. The pink color is also the line of the salinity interface with the TDS at 1,000 milligram per liter in the 2050. So we want to reduce the amount of the groundwater pumping in the area which expand the area of the saline water. So at the end, we have the number of the groundwater pumping in 3 parts by X criteria. So we propose that we have to reduct around maybe 66% in the northern part, and 40%, 32% for middle and the coastal part, respectively, to reach the sustainable use of the aquifer system in the area. So we will conclude with some conclusion here. So by analyze the groundwater pattern in each zone, and also combined with the satellite analysis and also statistical data, can verify the groundwater abstraction by the pattern and also the distribution. The estimate mentioned that one household uses around 2.2 cubic meter per day during the dry season. So it's close with another estimation of in 2010. However, the total groundwater abstraction is increased around 2 times compared with the estimation in 10 years before, due to the increase of the number of the wells per house, and so the number of the households of the province. And the saline groundwater distributed in the most area of the top aquifer, and in the north part of the second and the third aquifer. The saline groundwater have the tendency to move toward to the depleted cone due to the groundwater level drop in this area, and groundwater depletion also occurs in the coastal and the middle area. And also by using the groundwater abstraction as the estimate sustainable use, the aquifer system will reach to the new equilibrium state to control the saline groundwater movement in the saline fund areas. So the estimation also can check by the water balance analysis. So some other research, they set the shape view by the lateral recharge. So it takes around maybe 120,000 cubic meter per day in the study area. So with this number, groundwater abstraction can supply only for the domestic use in the coastal area only, not including the middle and the northern part. So in precision, now the Vietnamese government still define the yield for limitation of groundwater pumping based on the drawdown by the distance 30 meters from the land surface. In the next 10 or 20 years, it depends on the area. So this condition show a very high sustainable yield around for the area. The estimate is around 800,000 cubic meter per day. So it will need many problems of the saline movement and so the definition of the storage based on the estimation and so other research. So but this research proposed a sustainable yield based on the current pumping network. It takes about 155,000 cubic meter per day. This number can satisfy the domestic use with the normal standard and a proportion of the agricultural demand. If the government can propose some suitable adaptive measure, groundwater upstream in future can cope with the sustainable yield. Actually, in another part of my research, we also develop some scenario of the measurement and also climate change to see the how the sustainable yield change in the future and how the measurement can cope with the groundwater demand in the future. But because it limited the time, I only saw maybe a part of my research today. So thank you for your attention. It's the honor of my presentation today. Sorry for some in this time we disconnect with my presentation. So one more time, thank and waiting for the question here.
Yes, thank you, Dr. Ton, for giving a very insightful and interesting presentation to us, especially against the odds of the internet connections. So with that, may I open the floor to questions or comments from the audience? Please, if anyone have questions for Dr. Ton, please unmute yourself and raise the question. Thank you. Hello. So yeah, maybe I can start first. So Dr. Ton, so I have a very simple question to you as well. So the assessment is the assessment of groundwater use impact of sustainable yield of aquifer system in the coastal Vietnamese Mekong Delta. But we all know that the aquifers are interacting, underground, and then something is a little bit unknown. So what would be the future directions from your research that we can make for the scientific community? Please, Dr. Ton, thank you. Dr. Ton, can you hear me? Hello, Professor Sangap, can you hear me?
Yes, I can hear you, but probably Dr. Tuan has the connection problem. Yeah.
Yeah. So, Dr. Ton, are you still there? Oh, okay. So I think we also have time. now. So everyone, if you have questions to Dr. Tuấn, maybe you can write email to me or Dr. Tuấn as well, and I will divert the questions to him. I think today, because we have internet problems, yeah, so I think we can wrap up the seminar series now. So thank you, everyone. Please stay safe. And a bit before closing the session, may I announce the next presenters for WEM Seminar Series number 8. So please allow me. Okay, so everyone can see my screen now. So for our upcoming seminar series, which will take place next month in August the 4th, the presenters would be Mr. Sonu Kumar and Ms. Pradit Grace. So please, Mr. Sonu and Mr. Grace, so please take note of your time, date, and we're looking forward to receive your flyers and listening to your presentations next month. Thank you very much. So with that, I would like to close today's presentation. So thank you, everyone, again. Stay safe.
Yeah, thank you. Please stay safe and healthy. Bye.